So our next session is made up of a collection of highlight talks. So these will be talks by three leaders in the field of robotics, and it will be lightning round style. So unfortunately, we won't have time for Q&A between each session, but again, I encourage all of you to connect with our speakers at the breaks and lunch and the reception later tonight. I will introduce each of the speakers now so that we can quickly move between each one, and I'll introduce them in the order that they will be sharing. So first to present is Professor Jeannette Bohg. Jeannette is a professor of robotics at Stanford University and directs the Interactive Perception and Robotic Learning Lab. Her research explores underlying principles of robust sensory-motor coordination in humans and how we can implement them in robots. And research on this topic is at the intersection of robotics, machine learning, and computer vision. Her lab is specifically looking at robotics grasping and manipulation. After Jeannette, we will hear from Karol Hausman. Karol is a co-founder of Physical Intelligence, or PI, where he aims to bring AI into the physical world. And before starting PI, he was a research scientist at Google DeepMind and adjunct faculty here at Stanford. And he's enthusiastic about investigating foundation models for robotic decision-making. And our last speaker in this segment is Dr. Fei-Fei Li. Fei-Fei is the inaugural Sequoia professor in computer science here at Stanford and a founding co-director of HAI. She served as director of Stanford AI Lab and spent some time at Google during her sabbatical. Most recently, she is co-founder and CEO of World Labs, a company focused on spatial intelligence and generative AI. And like James, I've had the pleasure to work with Fei-Fei here at HAI. It is incredibly inspiring, and I'm excited for you to hear more about her work today, along with all of the other speakers. So let's first welcome Jeannette.
Hello, everyone. Good morning. When was the last time you looked at YouTube to learn something new? Probably not so long ago. Yeah, maybe this week, last week. Yeah, so I want to talk today about how we can bring robots to maybe learn new skills from YouTube. And so I will start with talking about why we need to scale up data in the first place, and then why robots looking at humans doing things might be a good idea to get there. So let's talk first about why scaling up robot data might be important. So as you've undoubtedly been aware of, is that foundation models have really changed how a lot of fields in computer science are doing research as well. And this term foundation model has been actually coined in this article, if you're interested. It's actually more like a book, to be honest, and was written by many different faculty here at Stanford. And the way foundation models are defined in this article is as large models trained on vast quantities of data, often using self-supervision, therefore avoiding the manual labor of labeling. And importantly, they can be adapted to a wide range of downstream tasks that they haven't even been trained to do. And so here are some examples for these models, these stochastic models that take an input and produce an output. Of course, you all are familiar with things like ChatGPT and Claude that take us input text and output text, or with systems like DALL-E that take us input text and produce an image, or the most recent versions of it that Dorsa showed this morning, where you can take an image and produce a Ghibli Studio style version of it. Or there are things like Segment Anything or things like Clip that are really useful in robotics as well. So these are all foundation model examples that are coming from the area of computer vision or natural language processing. So what would be a robotics foundation model is the question I want to ask here today, and the reason for why we might want to scale up data collection. So first of all, let's look at what robots can do today. So here's an example from our friends at Google. Actually, Karol was part of this team who did this work on RT2, that at this point, if you remember, it was New York Times front page news, where this robot could pick up the extinct animal. And the exciting thing for roboticists and non-roboticists alike was that it could do this inference from extinct animal to plastic dinosaur toy that is in front of it. But I also want to get your attention a little bit to the kind of manipulation it's doing, it's a pretty simple grasp. It's also a sped up video. And so what this shows me is that we're still very much behind things like this, of a human, for example, repairing this iPhone and using tools, prying things and small items out of this electronic device, using screwdrivers to unscrew minuscule screws and so on without actually breaking them. So very far away from this. We're also very far away from opening an oyster like Rodney showed earlier today. And we're still very far away from just doing everyday human tasks that people are doing in their everyday environments, in their houses, with whatever objects they find. And so the reason for maybe thinking about how we can scale up data collection and robotics is to also have a kind of robotics foundation model that can actually emulate these sensory motor capabilities. And we want this foundation model to generalize over all the different objects that are out there, environments, different robot embodiments, but also, of course, all of the different tasks that are out there. And to get there, the main bottleneck towards this goal is really a lack of data at the moment. And to hammer this in a little bit more, here's a very simple bar plot for you to look at that compares the data that is actually used in the area of natural language processing for these two models, and the data that we have publicly available in robotics right now. So we have a very stark difference there. And if you actually wanted to scale up the data in robotics to the same amount of data that you have in NLP, assuming that these are the same problems or these problems have the same hardness, you would need to increase the current data collection effort by a factor of 15 million, right? So these are 7 orders of magnitude, actually. Okay, so I would claim this is pretty much impossible on real hardware, but we're trying anyway. So here's an example of an effort that was spearheaded by Chelsea Finn's lab and that many other labs, including my own, was part of, where we lugged a robot into different people's apartments and have them demonstrate tasks that this robot would do in different, bathrooms, kitchen, but also our lab space. And why do I think this is not possible to scale up? Because this is really how this looks like. So this is Jimmy Wu, one of my lab members who has been the lead for this project in my lab. And he's here demonstrating to this robot how to unload a dishwasher. And you can see that he's really good at it. He makes it look very easy. But in order to be, for example, on this paper, you had to do 40 hours of this. Full-time week, 8 hours a day for 5 days. Okay, and so this is, by the way, the robot that we lugged from place to place to do this data collection. And so in order to kind of get a sense of how hard it is to actually do this data collection, try teleoperating a robot today during the conference. So Jimmy is actually out here today, and he will let you teleoperate TidyBot. And he has built this really cool phone-based teleoperation interface. And he's, again, really good at it. But I think you should get an experience of what it actually means to teleoperate a robot and to collect this data. Okay, here's some other ways on how to collect data, maybe a little bit more efficiently. Here, for example, a work from Shuan Song with these handheld devices. Or we could just pool robot data together from all of these different robots. Then, of course, you have this issue of learning across different robot embodiments, which is a very interesting research problem, but still unsolved. You could also do something like taking a vision language model as integral part of your robot architecture, which was done by Pi0 and Gemini as well. That helps to fight this bar plot and this factor of 15 million. You could also try to use simulation to generate more data. Then, of course, you have to fight against the sim-to-real gap, which is especially dire for these kinds of environments or objects and materials that are deformable or dough or liquids. Or you can do what I'm suggesting, or I want to tell you a little bit about today, which is learning from human videos. So here's 2 data sets. They are called Ego4D or Epic Kitchens, and they have recorded people from an egocentric viewpoint actually just doing their everyday things like cooking or doing crafting, and they're wearing a hat, basically like a helmet or something like that with a camera to film what they are doing. And so wouldn't it be great if a robot could learn from these types of videos? Because first of all, videos are way more abundant than robot data. So that's one fact. And then also iPhones are also, for example, just to take one brand here, are way more abundant than these handheld devices like the Yumis that I showed earlier as well. So there's really an opportunity here to scale up data collection with a person just having their phone, which they anyway have in their back pocket, to film themselves doing something and thereby teaching a robot. So I want to show you one particular work today that we have done in my lab that brings us, I think, closer to this step. So it's a novel data collection method that enables using only human videos to train a robot policies. And so here's just like a small table comparing to all the related work that is out there, because of course training a robot with human videos is not a new idea. And so we are really like one of the few that only needs human videos, can deal with deformable objects, and is also a closed loop or produces a closed loop policy. And the benefits are that it dramatically increases the possibility of collecting data sets and also the diversity of the data sets. You can deploy policies that you learn from this data zero shot on any robot, and it's really simple. So here's the kind of data that my student collected. This is how it looks like. You see it's like inside, outside, different surfaces, people in the background or not. And so we take this data, these human videos, and we do something very simple. We do a data editing method where we essentially track the human hand using some method called a human hand tracking method to get this hand pose out. Then we use an image inpainting method to just remove this hand. They're working really well right now. And you see like it produces an image where you can't tell that it was ever a human hand in there. And then we render in a robot, the robot that we actually have and want to train, with the same hand pose, doing the same task in this image. And the output is now a data set that actually has robots in there instead of human hands at all. So this is kind of a close-up view of how this looks like. So again, these are videos that are edited where the hand is removed and you only have the robot in there. And you see there's like some noise in there if you look very closely at the object and the hand, but it looks pretty good. And also, you can do it with any kind of robot that you actually have. So on the left here, you have the human video, and then you can use this method to inpaint any of the robots for which you have basically a CAD model and the kinematics. And it looks pretty good. So then you use this training data, and you train an imitation learning policy, whatever you like, whatever is out there. And then you, at test time, basically take your robot, we overlay it again with the virtual robot, which is very fast, and just run the policy. And this is how it looks like, zero shot deployed in new scene. So here we basically put our robot on the lawn behind our Gates building where we do our research, and you see there are lots of cars and people walking around in the background, or in the other video there's someone having lunch in the background as well. Or here, we also show that we can really do this diversity of tasks even with deformable objects or with multiple objects, which is really hard to do with other methods. Okay, so this was a little sneak peek into the work we're doing towards letting robots learn from, at some point, YouTube. And just like you, look at YouTube to learn a new skill. And we keep on working on this idea. So here's just a sneak peek on some work that we're doing right now with more complex hands, where we have a multi-fingered hand doing things even while a person is like perturbing it or disturbing it. So I talked a lot about data collection today, but I think there's so much more missing than just scaling up data that is important to look at. We need new policy architectures that can actually squeeze out much more from the data that we have than we can right now. Maybe we need some kind of DeepSeek of robotics, if you want. We need new algorithms that can actually that can do online adaptation and not just like use a policy that is deployed without ever improving it again. We also need way better methods and way better data to use tactile sensing as well. Robots also need a sense of touch to do certain tasks that are just impossible to do from visual information. And also what we need is way better hardware in robotics. So even in research, we are running against very brittle hardware, while there could be so cool ideas like this roller grasp. I see Ken Salisbury here, who he and his students, they developed this, which is such a cool idea. Instead of having fingertips, you actually have active surfaces or wheels inside of your fingertips, and so you avoid difficult problems like context switching. And these are the kinds of designs that we need more of in robotics. We don't need humanoids, right? Like we can be very creative of how our robots look like. And so also on the other side, you see the mobile-based platform from Tidybot, which you can see today in the demos. But today I focused a little bit more on data collection, especially through human videos, and I hope you learned something about this work, and I'm happy to talk more about it. So these are my fabulous students. Thank you very much for your attention.
Hi everyone, I'm Karol Hausman. I'm a co-founder of Physical Intelligence, and today I wanted to tell you about building physical intelligence. So over the past year, I experienced building physical intelligence in a few different ways. First off, we started a company called Physical Intelligence. We are over 30 people now with lots of robots, lots of data, training big models, trying to get them to perform quite complex tasks. If this is something you're interested in, please reach out. I also experienced physical intelligence in a much more visceral way. I have a 1-year-old baby. And it's super cool to see her emerge in physical intelligence. But if I were to take both of these events and learn something from them, if anybody in the audience is considering having a baby and starting a company at the same time, please talk to me. This is a horrible idea. I will do anything in my power to discourage you from doing that. So at Physical Intelligence, our goal is to build a model to control any robot to do any task. We think of it as a foundation model that would allow us to lower the barrier of entry for any new robotics application. Now, the main idea behind this is to train a big generalist model across many different tasks and many different robots. The current incarnation of this idea is called the Vision Language Action Model, or VLA. The way they work is actually very simple. They're analogous to vision language models. So if you're familiar with vision language models, they take an image as input, as well as some language, and then they try to predict the output, usually also in the form of language. Now, it turns out that you can cast many different vision tasks into this format, and because of that, these models can absorb a lot of data and generalize much better than specialist models. And it turns out that we can basically take that recipe and translate it to robot control as well. So for Vision Language Action Model, instead of a static image from the internet, we would have the camera feed from the robot. You would ask it some kind of task, for instance, to fold a shirt. And then given that it was pre-trained across many different embodiments, across many different tasks, it should be able to interpret that command correctly and then start outputting the actions to actually accomplish the task that you ask it to do. So last year in October, we released our first model, our first vision language action model called Pi0. And here's a little demonstration of what this model is able to do. Oh, actually, I thought there would be no sound, but you can hear a little bit of sound. So here's a task that we haven't seen robots do, where you have a mobile robot that is fully controlled by our Pi0 model, that takes laundry out of a dryer, puts it in a basket, brings the basket over, and then folds it into a nice pile of laundry at the end of it. I wanted to tell you a little bit more how this model works. So it's a generalist robot policy that is pre-trained across many different embodiments, so single-arm robots, two-arm robots, mobile robots with lifts, and all kinds of different ones, across many different tasks as well. Then we also use pre-trained internet-scale data from Vision Language Model, as well as open-source data. And we end up with our big Pi0 Vision Language Action Model. Then we can take that model and evaluate it zero-shot for the tasks that this model has seen in the past. But we can also go through the post-training process to get it to perform really complex tasks, such as laundry folding that you just saw, to get it to hone into very specific behavior, or to onboard new tasks that are simpler for the first time and onboard them very quickly. So before I tell you a little bit more about what I believe made this model really good, I wanted to show you some examples, some highlights of what the model is actually capable of. And I'm going to focus on the task of laundry folding because I think it's quite representative, but it can do many, many more tasks than that. So here is one example of the robot trying to fold a shirt. This is a different robot. This is 2 static arms. And you can see the level of manipulation it needs to perform to find the right corner. So initially, it grabbed the T-shirt from the wrong side. Then it was able to kind of turn it upside down a little bit, grab the right corner. Eventually, it gets it more or less right. It needs to adjust the sleeve a little bit. And then over time, it gets the 2 corners correctly, brings the shirt a little bit closer so it can take the other side of the shirt, then folds it in half, taps it a little bit, straightens it out, and then folds it in half again, taps it a little bit more, brings the pile over, puts the shirt on top of that. Let's look at a few more. This is a completely unseen shirt. So it takes a shirt again. It kind of makes you appreciate the complexity of this task. And it tries to kind of flick it out, but then it struggles quite a bit. You can see it trying to do it over and over again. But then it actually realizes that something is off. It probably doesn't grasp the right corner. So it pushes it a little bit away, grasps the right corner, and then starts folding it, and then ends up with the same nice fold that you saw in the previous video. So folds it in half, will bring the pile over, and keep on going. Here is another example of the robot kind of being stuck in this little motion, trying to flick it out, but then eventually realizes again that something is a little bit off, so it puts it the other way up, and then starts folding the corners. We have many more examples like that, and I encourage you to check out the website to see more videos like this. Here is one more example of how these models can handle interruptions. So here the robot is minding its own business, trying to fold the clothes, and then our researcher, Michael, throws another shirt onto the table. And the robot is still able to know what to do in this situation. It just wants to fold the shirt, just let it do it. We can do more interruptions, things like the robot is trying to fold the shirt, is about to fold the sleeves in, and then mean Michael comes in again and unfolds it. So the robot continues, just flicks it out again, starts with folding the other side. Michael undoes that one. It continues with the first side. Then it turns out that the corner got a little bit off, so the robot straightens this out, and Michael keeps on messing with it. All right, so now a little bit more about what I believe actually made it work. So I think the really important idea here was this idea of pre-training and post-training. This is something that you might be familiar with from large language models or vision language models, but it turns out that it translates quite well to robotic control as well. So we do this 2-stage training, where first we do pre-training, where we use a lot of data across many different form factors and many different tasks. It's around 10,000 hours of data of many different robots doing all kinds of different tasks. We are not very careful when it comes to filtering that data. We just want to crump as much data into the model as possible to give it some kind of notion of how you should move to accomplish different tasks. But then on top of that, we also do a post-training process where we try to home in a specific behavior. So here we collect orders of magnitude less data, but it's data that we care much more about. It's much higher quality data of very consistent strategies. We do this for laundry folding or for tasks such as building a box that is also quite dexterous, and you kind of need to get everything right to make sure that the task succeeds. And it turns out that doing both of these together actually helps quite a lot. So here's a little bit of, of quantitative evaluation of this. So we'll be comparing pre-training and post-training together versus not doing any pre-training, so just take the curated data set of these 20 hours where you have basically really, really good behavior. And we'll be also comparing to no post-training, so just train on all the data and don't do the last part. And it turns out that both of these really, really matter. And if you don't do the robotic pre-training and just train on this very curated data set, then even though the data set is kind of perfect, you don't really know how to react if something goes wrong. You don't know how to make corrections if you fail, for instance, with folding a shirt. If you just do pre-training and don't do post-training, then it turns out that you don't really know what kind of behavior we actually want you to do. There's all kinds of different behaviors that are embedded in the data set, and you don't really know what behavior to home in on. So this is a little bit about Pi0. Now, this is the very first model that we released, but we also wanted to make sure that you have a chance to use it yourself. We are very early. These models still don't work to the extent that they should work. So we wanted to give it to people, see how you can use it, and see how well it could work on your robot as well. So the answer to this question is yes, you can use it. We open source basically everything. We open source the model, we open source the code to fine tune it. We also make it as easy as possible for you. So we release a few different checkpoints, some of which are pre-trained on academic data sets, so you can try it on robots that you have in your lab. There's many labs who already have tried it. We also showed many examples of how you can integrate it with different runtimes. So I encourage you to try it out and tell us how it goes for you. On top of that, we also started a partnership program with different robotics companies that reach out to us and try to use our models for their robots. So here is a humanoid robot called Astrobot that is running basically this model that was fine-tuned on a little bit of their data, doing a task of simple coffee making. And there is many more partners that we are working with to try to make sure that these models are general enough so that they can be applied across many different embodiments. Now, since then, this was October last year. Since then, much more has happened. We developed many more things. There's more things that we're going to release soon. Two things that I wanted to emphasize is, first, we developed much better action tokenizer that allows us to train these models 5 times faster, which means our iteration cycle went from weeks to days now. We also start to see that you can talk to these models and take advantage of the fact that these are pre-trained large language models. And here's an example of us doing that, where you see Chelsea in this video asking a robot if she can have a sandwich with roast beef and cheese. And then the robot breaks down that task, talks itself through language of what are the different subtasks. And because the model is able to follow the language instructions, it then directs the robot what to do. And it's able to handle much more complex prompt than it was able to do in the past. So at the end, I wanted to take a step back and kind of see where we are at today and what is missing. So far we've shown a prototype of a generalist model that is trained across many different robots that starts to do some really interesting tasks. So it shows some kind of sparks of physical intelligence. And it's actually pretty magical to see them, especially live, when you see the robot kind of struggle with laundry and eventually get a nice pile of laundry towards the end of the task. I believe we also start getting the first signs of a recipe that is scalable for training robot foundation models. This pre-training and post-training paradigm, I believe, is here to stay. There's many more things to figure out, but I think we have some first gist of what that recipe could look like. Now, having said that, we are still very, very early. And if you're on Twitter for too long these days, you would think that all of this is solved and it's just a matter of scaling up data collection. I don't believe that's the case. There's many things that are missing, things such as these models don't generalize as broadly as they should. If I were to give you that robot and try it in your home to fold your laundry, it probably wouldn't work. You would need to collect a little bit more data. We need to get them to generalize much more broadly. We also need to improve robustness of these models and get them to perform at much higher clip. Right now, our best models perform at maybe 80% or 90% success rates. We need to get them to much higher success rates to be able to actually make these models useful. And then lastly, we also need to have a better understanding of what it would take to actually achieve those goals, to get to a certain level of generalization or to a certain level of performance, and understand what kind of data it would take and how much of that data it would take. Now, having said all that, I feel very optimistic. I think based on everything we've seen, especially for some of these tasks, I think we're making a ton of progress, and there's a ton of hope and excitement that this problem is solvable. Now I just need to make sure that the other physical intelligence does the same, but it might take a while. All right, thank you.
Thank you, Rodney. Thank you, Jeannette and Karol, for such great talks. Okay, so I'm just gonna start my talk, and following what Rodney was talking about, we had great dreams of robotics, especially by Hollywood, telling us what robots will do. And by and large, even though this is a few years older, robots still are in this stage, right? Compared to robots that do all the chores for us, we're still in this really uncomfortable state where it doesn't quite work. And there are many reasons. I'm not going to repeat all the great reasons of why we are still in the early stage of robotic research. But one of the things that we know for the past few years is that most of the robotic research today are still in these relatively small ad hoc environment, and the tasks are relatively simple, still in pick and place and small scale, and mostly set up by experimenters in their particular environments. And we haven't seen the kind of scale in terms of both data and benchmarking. And we know that real world, where we want robots to truly work in, is much more complex. It is, it's dynamic. It has a lot of large variabilities. It is interactive. It's social, as well as it has a lot of different multitasks. So my own, in the past decade, I have been also doing robotic learning research in addition to computer vision. And one thing I would love to get inspired by is the effort of AI in the field of computer vision and NLP in the past decades plus, is this effort towards large-scale learning and benchmarking towards important North Star problems, such as what we see in vision as well as NLP. So today I'll just go over a few projects by my students and collaborators in my lab, and they more or less share one theme, which you have heard already from previous talks, is the data-driven approach to robotic learning. And the first project is a project called Behavior. And what Behavior focuses on is creating a simulation environment to generate a ton of simulated data so that robots can get trained by a large amount of simulation data. And we pay particular attention in terms of the kind of behaviors that we want robots to eventually learn. We heard a lot about these pick and place and all that, but what we would really love robots to do is to help humans in everyday environments. And that's how we picked 1,000 human everyday tasks and simulated those tasks in this behavior environment. Specifically, the 1,000 tasks are long horizon tasks such as cleaning after a wild party, making beds, making sandwiches, and all that. And we collected 50 real-world 3D scenes, as well as more than 10,000 3D objects with all kinds of properties, and then collaborated with NVIDIA using a very robust physical simulator. So these 50 different scenes come from different environments, from office to restaurants to home apartments to grocery shops. These 1,000, sorry, did I say 10,000? 1,000 plus 1,000 plus categories of 10,000 plus objects have very detailed 3D models. They come with more than 30 different properties, from articulation, deformability, different temperature states, and all this. So if you put together these large scene environments, 10,000 objects, and 1,000 different human tasks, you basically can have a large-scale simulation environment of infinite possibilities. And this is really the goal. We want to use this kind of huge data to drive robotic learning and also to benchmark eventually robotic learning. And of course, it's also important to point out that we need a physics simulation, and this is a collaboration with NVIDIA. We work with their Omniverse team and created this simulation engine called OmniGibson. And one thing it's important to point out is that eventually we have to take simulation to reality. So sim to real is part of our efforts. At least we begin by having a physical environment in our lab to work hand in hand with our simulation. So what you're seeing is the basement of our Gates building that we created a apartment, and this is the robot performing different tasks or learning different tasks. So that's the first project called Behavior. We hope to invite the entire field of robotic learning to use this simulation and our data to work towards these really hard, long horizon problems like 1,000 home tasks. And we're hoping to, we have been releasing our different versions of behavior in the past couple of years already, and we're hoping to create a challenge at the end of this year, so please stay tuned. The second project I want to just quickly talk about is what we call digital cousins. And this is really thinking, this is led by these two students. And this is a project that's inspired by behavior. Now that we have simulation environments that has so many kind of objects, environments, configurations. We can randomize lighting, randomize texture, randomize different states. So it's such a rich potential resource for learning. And one of the hardest things in learning in robotics is if you put a physical robot in a physical environment, you don't get that much variability in learning, and that's downstream, that's going to cause hard generalization. So we started this project called Digital Cousin, and the idea is that given an inspiration, for example, a physical set of sofa, we could actually ask the digital database to give the robot a ton of similar objects and their configurations, both in terms of appearance as well as in terms of affordance. And with that, we can drive learning better. And here's an example of a student looking at a particular part of the kitchen, and this is the real scene that they captured. And then, given the real scene, we can actually go to our database and really, instantiate so many different kind of digital cousins, and then drive the learning through these different examples. And the idea is that if a robotic policy is learned through just what we call digital twin, the same example, then the performance degrades as we want to generalize to different examples. Whereas if it's given the digital cousins to learn, your policy can generalize a lot better, and the degradation is a lot less. And this is really, at the end of the day, it's a simple idea. It's just the idea of data augmentation. But because of these simulation environments, we can actually do that. And this is just a particular example of robot learning through digital cousins and being able to perform tasks like opening doors. The third project I want to share is a different way to look at data collection, and it's called DexCap, and it's a collaboration with Karen and as well as our co-advised student. Here's the idea. I know that Rodney said 5 fingers is an evolutionary accident, but whether it's accident or not, it's actually an important apparatus that humans use to do a lot of manipulation tasks, and collecting data through our 5 fingers is an important part of robotic learning. And it's not easy, so many efforts have been made in the past about this, and this is the latest that we use this particular glove to collect both hand motions as well as point clouds. And the one nice thing about this setup is that the battery can be put in the backpack, and the students here have collected a large amount of bimanual hand dexterous hand data in terms of robotic manipulation tasks, and then we use this data to drive the learning of the robots. I'm particularly fond of this project, not because it really boiled the ocean and solved the problem of hand manipulation in robotics. It is actually shows how hard it is. We're truly at the beginning of this kind of research, and it also shows that robotic learning is not all about foundation models. Learning very meticulous gestures of hands and using the correct hardware is actually part of a very difficult journey still. And this is just an example of bimanual tasks performed by our robots, having learned through the data collected by humans and use imitation learning to perform these different tasks. Last quickly, this is a project called VoxPoser. It's actually a combination of 2 projects called VoxPoser and Recap. And this is led by my student Wenlong. And this project is very much in spirit of what we have just seen both in Jeannette and Karol's talk, is really thinking beyond data we can collect in the lab or even in a confined setting, is to take advantage of the great progress of the LLMs and VLMs these days in the other related field of AI, and see if we can almost bypass some of the own learning and taking these large models to help robots to perform tasks. In this particular project, VoxPoser, the robot is given the instruction of open the top drawer, but also watch out for the vase. And in this case, we use LLMs to parse the instructions and also use a visual language model to map out the motion map by actually detecting different parts of the scene, understanding the object's identities, and create a motion map that is optimal for this particular task. And you just saw the examples. Wait, let me see. Never mind. Here are the different examples of different tasks that's given language instruction, and the robot is capable of performing that without learning yet again through more data. So this is pretty much zero shot coming from the large language model as well as a vision language model. Of course, we can also take this to even more complex, longer horizon tasks by adding the temporal dimension. So this is a follow-up work by my student Wenlong after the previous work, of particularly highlighting the affordance points or the key points of the scene and learning the trajectory of the scene by using these multimodal language models in the 3D space-time. And then after that, using these models to do the constraint optimization and be able to do a policy planning for a setup like this. And here you're seeing a particularly difficult setup because it's bimanual. It has multiple objects. It was being disrupted by the experimenters. And these objects, some are deformable, some are rigid. So it's different types of objects. And these examples show that we can do multi-stage, long horizon, reactive, deal with disruptions. It's bimanual, and the objects are in the wild. So I want to actually finish with a question. You've been hearing a lot about so what, the robotics, but the question is so what, right? As a technologist, we might be just innately excited by the so what of, I got this robot to work. But here we're at HAI, Stanford HAI. A lot of what we do are motivated and inspired to do good in our world. And the same is true with robotic learning. We have a lot of so what. For most of our graduate students, the so what is laundry folding and dishwashing. But there might be more than that. And especially in the world of robotics, we've already heard there's a lot of talk about threats to human society, like labor market. And if you see, whether you call it hype cycle or dystopia cycle or whatever the cycle is, we are now in the middle of this, and we hear these pretty intense concerns about robots taking jobs away. And I think it's actually important to recognize the labor disruption or transformation as human society invents technology and innovates the way our economy works. We are always facing with these phases of economic and labor changes. But here at HAI, one of the founding motivation or pillars of intellectual North Star for us is actually not about AI replacing human. We want to replace the word replace and put augment in that. We do believe AI is a tool, robots are tools, and they should not, like Rodney said, take our agency away, but augment us. So I want to end with this one pretty dramatic experiment or project in my lab where we use human brain interface and to demonstrate that one day robots can be driven by just human thoughts alone. And because of that, there is a possibility to actually help the most vulnerable, severely paralyzed patients. In this case, human thoughts are collected non-invasively through EEG caps. So these are brain electrical waves. And we trained the different movements of the robotic arm by collecting these brain waves. And the idea is that we can turn brain waves into neural network, and these are atomic movements such as pick up the bottle. And then after some longer, training, tens of hours, here's an example. In this case, our experimenter, wearing the EEG cap, was able to remotely drive this robotic arm to make a Japanese sukiyaki meal completely by thoughts without touching any of these things. It's actually, you can do it remotely. And that is, this is very much experimental. It's very much in the demo stage. There is a lot to be worked out, but this does excite me. This is the kind of ultimate so what, is that we can create these kind of robots to help people who are most in need. Thank you so much.